Hello class, sorry I can't be here today. Today we're actually going to go out of order from our initial plan, just because I kind of figured this would be easier for you to learn on your own. And we're going to do 4.3.1, which is trigonometric functions at any angle. We will still study linear and angular speed, but just not today. So first, whenever you are doing trigonometric functions at any angle, that means that we can actually go outside of the first quadrant. So you're going to see examples like this, or problems like this, where it says plot the point 4, 3, and then determine all 6 trigonometric ratios. So if I plot the point 4, 3, 1, 2, 3, 4, and 1, 2, 3, I'm right here. This one is in the first quadrant. And technically, my line passes through that point. But if we know that we pass through that point, we can turn this point, this line segment right here, into a right triangle. So whenever you make your right triangle, you always want to make your right triangle with the x-axis. That's something to definitely make a note of. You always want to make your right triangle with the x-axis. And let's label it. Since our x component was 4 and our y component was 3, those are the 2 legs of the right triangle. And then we can Pythagorean theorem, 4 squared plus 3 squared equals 25 squared, so the third side is 5. And then we can go through and find the sine, the cosine, and the tangent of theta. And then we can just flip those fractions. So here's our theta. It's 3 over 5 for sine. Cosine is 4 over 5. And then tangent is 3 over 4. And then we can find our reciprocal functions. The secant of theta is 5 over 3, or the cosecant of theta is 5 over 3. The secant of theta is 5 over 4. And then the tangent of theta is 4 over 3. When you're in the first quadrant, every single trig function that you come across is going to end up being positive. Now, when you rotate outside of the first quadrant, that's when life gets a little interesting. So, determine the trig functions if you pass through -2, -1. So let's look. -2, -1 is right here. In fact, let's just make that a little bigger so it's easier to see. So this is the point -2, -1. Your picture doesn't have to be exact. And again, your x component is -2. Your y component is -1. So when you're doing this, you do it the same way you did the other ones. You've got sine of theta, you have cosine of theta, tangent of theta. Now technically, the angle that you're looking at, again, starts here on the positive x-axis and rotates all the way that way. But when you make your triangle, you make the triangle with the x-axis, no matter where you are. You're always dropping down a perpendicular from your point to the x-axis. So when we evaluate, we're trying to find this theta, technically, when we turn this into a right triangle, the trigonometric ratios of this angle will be the same as the trigonometric ratios of this angle down here. It's whatever angle you're making with your positive x-axis. So it's Pythagorean theorem. 1 squared, or -1 squared plus 2 squared, both of those are going to become positive. So that's 3 squared. Or that's 3. So this is going to be the square root of 3. And it's okay that you have radicals. Radicals are very common in this process. So sine of theta this time is going to be a negative. -1 over the square root of 3. And then the cosine is going to be -2 over the square root of 3. And then the tangent is going to be -1 over 2. -1 over -2, which ends up becoming positive 2. And then let's be good math students and rationalize our denominators, because we are always going to be good math students and rationalize our denominators. Whenever you rationalize your denominators, your fractions are going to stay negative. And then it told us to find all 6. So we'll flip these again. Flip the fraction before you rationalize it. It's a lot easier. So your cosecant, your secant, you flip the cosine. So it's the square root of 3 over 2. Again, still negative. And then the tangent of theta is 2. So, recapping what we talked about so far, we're going to plot our point, and then we're going to make a triangle with the positive x-axis. So let's talk a little bit more in general. In general, looking at both of these examples, your sine value was, in both of these cases, was your y value of the point, 3 or negative 1, over what we call the hypotenuse. If we think about this as a circle, we can also call it the radius. Either one. Your cosine was the same as your x value over your radius of your circle or your hypotenuse. And then your tangent was just y over x. So when you do these on your own, if you remember this pattern, you actually don't have to draw the picture, but it's nice to get in the habit of drawing the picture. So, for this last one, the point 8, 6, negative 6 is down here. And again, you make your right triangle with the positive x-axis. Technically, you could think this angle rotates all the way around, but those trigonometric ratios are going to be the same as that angle right there. So, when you're doing your sine, cosine, and tangent, again, you've got to find that radius. So you have 8 squared plus negative 6 squared. And again, when you square that negative, it's going to become a positive. That's 8 squared plus 6 squared is 100. And then when you square root that, you get 10. So no rationalizing of denominators here, but we will have to reduce your fraction. So this is 8, and that's negative 6. And again, sine is y over your hypotenuse. So negative 6 over 10, and that reduces to be negative 3 over 5. Hey, it's the same as the first one. How convenient. And the cosine is 8 over 10, your x over your hypotenuse, which is going to be 4 over 5. And your tangent is going to be negative 6 over 8, which is negative 3 over 4. And then your secant, cosecant, and tangent, your reciprocals, you can just flip those. And this brings us to another batch of generalities that we want to think about. Because a lot of times, I'm not going to give you a point. You're going to have to figure out the information, some of the information on your own. So looking at these 3 examples, let's zoom out a little bit here. So when we look at these 3 examples, we have something general that we always want to think of. And this is going to be something that you're going to do so much that you're just going to end up having it memorized. So if we keep track of what quadrants our trig functions are positive, then we can kind of expedite a lot of this process for ourselves. So this was in the first quadrant. This point was in the first quadrant. And if you notice, sine, cosine, and tangent were all positive. All of them were positive here. And then in this one, our second example, we were negative. We were in the third quadrant. So let's draw the third quadrant here. And if you notice, sine and cosine were negative. Tangent was the only positive one. Tangent was the only positive one. Again, I'm tracking the positives here. And then in this last one, looking at sine, cosine, and tangent, it looks like sine was negative, cosine was positive, and tangent was negative. So the only positive one here was cosine. And then we didn't do an example in the second quadrant, but using your deductive reasoning skills, if tangent was positive here and cosine was positive here, sine is going to be positive here. And that's, again, because your y value is positive in this quadrant, but your x value is negative. So, if you keep in mind this, whenever you're doing these types of problems, you have all the trig functions are positive in the first, and just sine is positive in the second, and only tangent is positive in the third, and cosine is positive in the fourth. It'll help you when you are doing this next batch of examples. And there's an acronym. The acronym is All Students Take Calculus. So you can kind of think of that when you're doing examples and problems like this next batch. So if I tell you that the tangent is 5/12 and the sine is greater than 0, find the exact values of the remaining trig functions. So let's look. Let's draw a picture. And now we have to figure out what quadrant we're in. So it tells me that the sine is positive. So let's keep in mind all students take calculus. It tells me the sine is positive. And then just thinking about the numbers here and then in general, the tangent here is also positive. So the quadrant in which the sine and the tangent is positive would be the first quadrant. So I'm just going to draw this. Draw my right triangle. And here's my theta. And I know 5/12. Well, that's my opposite, and that's my adjacent. So that's 5, and that's 12. And if you know your Pythagorean triples, Pythagorean theorem tells us that 5, 12, and 13 make a right triangle. So then we can find whatever trig values we want once we have our triangles labeled. In the directions, I said all of them. I think on your assignment, I made you just pick one. But the sine would be 5/12. The cosine would be 5/13. 12/13, and then the tangent of theta would be 5/12, which we already knew. But sometimes I just get in the habit of writing them down. And then the cosecant of theta is 13/5. The secant of theta is 13/12. And then the tangent of theta is 12/5. Let's do another one. This should be cotangent. I did that a couple spots, didn't I? My apologies. I did it everywhere. Sorry. Okay, let's do another one. So if the secant of theta is √3, and then the tangent of theta is less than 0, find the exact values of the remaining trig functions. So keeping in mind this again, I know that my tangent is less than 0, which means my tangent is negative. So, well, my tangent is positive here and here. So I don't want that. So I either have to be in this quadrant, in the second quadrant, or the fourth quadrant. And then my secant is just a positive number. I don't care what it is right now. But my secant and my cosine are going to have the same value. So wherever the secant is positive, the cosine is also going to be positive because those are the reciprocal functions. So that means we're in this quadrant where the cosine is positive. And cosine, if secant and cosine are reciprocals, that means that cosine is 1/√3. So 1/√3 adjacent over hypotenuse And then we can Pythagorean theorem that, and we end up with that side